In a series of previous videos, we showed that today's cryptocurrencies were very much of an overkill, as they implement a solution to the very difficult consensus problem. Yet, we saw that decentralized cryptocurrency design was a problem of consensus number one, meaning that it did not require solving consensus. In fact, a quorum-based decentralized system was sufficient to guarantee the safety of the system. Unfortunately, though, we also saw that such a quorum-based system was not scalable, which means that it would not be performant if it was scaled up to billions of users. Can this system be adapted to high performance for billions of users?
It can. Actually, our results show that it might work for an basically arbitrarily large system, even in the order of billions or trillions of nodes.
This is Matteo Monti, a PhD candidate of the IT school at EPFL.
Obviously, in order to achieve this, we have to first overcome the problem that Matej introduced, which is all-to-all communication.
Recall that in a previous video, Matej Pavlovic noted that for the system to perform correctly, any individual user that wants to make a transaction needs to broadcast his transaction message to sufficiently many nodes in the cryptocurrency system.
We want to be sure that when I want to spend some money, I'm going to inform the whole system about my will to spend that money.
And perhaps more crucially, to know that his transaction has been accepted, he needs to receive acknowledgements from sufficiently many nodes of the system, more precisely from a quorum of the system. Now, if there are only 100 people in the system, this can be done quickly. However,
if I had a system of 1 billion of friends, I'm very popular and have 1 billion friends, and I wanted to get some information from them, would I really need to talk to all of them to be sure, of what version of that information is correct? Probably I wouldn't, right? I could just pick some of them at random.
And if a sufficiently large fraction of the random sample has received the demand of transaction, then I could conclude that a large fraction of all nodes have also received the demand of transaction. Well, probably, with some high probability.
Yes, I might be very unlucky, and the outcome of my talking to some of them might be that I am convinced of the wrong version of that information. But the probability of this happening decreases, and this is due to what's called the law of large numbers. It decreases quickly with the more people I talk to. This is the main idea behind our algorithm. Basically, we trade performance for a tiny probability of the system failing, a tiny probability of security being compromised. That's what we do.
Now, I'm sure that many of you are uncomfortable with the idea of having systems that are only highly likely secure, as opposed to 100% secure. But crucially,
this probability can be made arbitrarily small, and specifically if we make it, small enough that, a number of attacks large enough to overcome the age of the universe can be done before the system collapses, we're still fine with it. And there's actually many other aspects of many other cryptographic constructions that still work in a probabilistic fashion, but we all rely on them because they are, extremely secure anyway.
Yes, a hacker may still successfully hack your bank account by guessing your password and being lucky. It's just that the probability that he is that lucky is extremely small. Well, at least if your password is not 1234.
So the idea behind our protocol is this. As Matej introduced, first we need to distribute the message. And in the closed system, small system solution, we will just have the sender send the message to everyone. Obviously, if I have to send a message to 1 billion or 1 trillion of other nodes, this is going to be infeasible, right? Because I would have to just talk to each and every one of them. So, the way we implement this in an efficient way is to just do what sometimes happens in reality, which we call gossiping. If I have, an interesting rumor about someone, I will tell some of my friends, and my friends will tell other friends, and so on and so forth until everybody knows about it. So basically, we do the same, and the message spreads exponentially through the system.
In particular, the exponential spread of the message means that even for billions or trillions of users, it only takes a few dozens of rounds of communication for the message to reach any user of the system.
Now at this point, the message has very efficiently been delivered to all the processes. And now we just need to make sure that if we decide to agree on a transaction, if I decide that this is the transaction that I officially receive that I can trust, then nobody else will agree on some other transaction. This is called consistency. In order to ensure consistency, I basically just need to go around and talk to enough many people so that I will know that I have a very small probability of me being convinced that the majority will agree that Matej wants to pay Alice, but he actually wants to pay Bob, right?
So to recapitulate, instead of broadcasting to every individual user, to scale the system, the idea is to use a gossip algorithm. And then, instead of checking that a quorum of processes received the transaction, a user will sample some of the processes and check that a sufficiently large fraction of the sampled processes have received the transaction.
In doing so, we proved that you don't need to talk with a very large number of processes. Actually, what we call samples are extremely efficient compared to quorums.
Yes, because the sizes of quorums and of samples actually play very different roles.
And a sample needs to be only large enough not to provide any intersection properties like quorums do, but only to be representative of the system. That is, to have a very low probability of having the majority skewed or giving me some information that is not actually true about the system.
In particular, this means that the sizes of the samples do not need to scale proportionally to the number of users of the system. But in order to make sure that the samples are sufficiently representative of the system, it is crucial to make sure that they are uniformly randomly sampled. A priori, this is a very difficult property to guarantee.
Luckily, there are some very good results in literature about this.
First, there's the easy case where there exists some list of users.
In literature, it's called the permissioned case. If every node has just access to a complete list of all the nodes that are taking part in the system, then obviously you can just, blind yourself, pick a random number and go to that place in the list, and you will have a process with uniform probability.
An efficient permission system for secure transactions is already very much of a breakthrough, as it can be applied, for instance, to the citizens of a country. But interestingly, Matteo Monti and his collaborators also proposed a solution for permissionless systems, that is, systems in which unknown users can enter even after the deployment of the system, as is the case for Bitcoin.
In the permissionless case, which is a system where the set of processes is not a priori determined, not everybody agrees on the set of processes, this can be more complicated. But there has been work in literature that allows us to do some form of sampling that is eventually uniform. It is asymptotically close to uniform. And that's good enough for us to do our sampling procedures.
And there you have it. Here is AT2, a large-scale, highly efficient cryptocurrency system that bypasses the need of consensus. This is a very spectacular result. And what's more, Matteo Monti and his collaborators also provided a proof of security of their protocol, even in the presence of numerous malicious so-called Byzantine users.
Yes, we do have a complete analytical tractation of this protocol, and we actually derived bounds on the probabilities of the security of the system being compromised.
Now, as opposed to the protocol itself, the proof of validity and safety of the protocol is not so simple.
In terms of energy efficiency, so our algorithms, they are negligible in that regard. Also, one other aspect that is important is that the solutions are very simple.
Some of the processes will behave in a way that's arbitrary. And here it's important to underline that arbitrary is different from random.